Okay, this is problem number 9 from chapter 20. Working it as an example problem. Let's see, it's on page 659. I'll read it to you first of all. Well, the assignment actually is the same for several of the problems. For problems 7 through 12, which 9 is in that range, design a welded joint to join the two members shown in the appropriate figure. Specify the weld pattern, the type of electrode to be used, and the size of the weld. In problem 7 through 9, the members are ASTM A36 steel. So let's write that down. Let's see, we'll start off with the fact that this is problem 20-9, and both the members are A36 steel. Let's see. Use the method of treating the joint as a line and use the allowable forces per inch of leg for building type structures from table 20-3. Now remember, building type structures versus bridge type structures. Bridge type structures are expected to move a little bit more than building type structures, so the allowable stress is a little bit lower. Anyway, problem 9 is figure 20-5, which is on the, well, I thought it was on the next page. Let's see, figure 20-5. No, it's on the same page. It's just above. Okay, so I will copy it down and solve this problem. Let's see, let's start off with the givens. Figure 20-5 with a 2,800 pound load. And I guess really the given should be expanded because A36, ASTM A36 steel is given as the material. We're supposed to find a weld pattern. And this is somewhat arbitrary. It's up to us to design it, depending on whatever makes sense. The electrode type and the size, essentially, of the weld. Okay, so to start off with part A, the weld pattern. Let me sketch the structure here. Let's try again. Let's make this a better vertical line. There we go. Let's see. There's a piece coming off. It's essentially a shelf. I'll break it here. The shelf has a height of 8 inches from the figure, and let's see, the width here of the rigid structure is 10 inches. And the rigid structure, by the way, is this component that I've cut off the top and the bottom of it, because I don't need to draw it all. But this is the part that's connected to ground that's ultimately supporting the load. But my choice for a weld pattern is to run a bead at the top and a bead at the bottom. That's my design. Now, you could potentially put a weld bead on the back side. You could put a weld bead on the inside. I'm not going to do that. I'm just going to put one at the top and the bottom because that's probably the easiest to do. These will be fillet welds. And remember, fillet welds are really the only welds you need to design. Groove welds, if the groove goes through the material where you have 100% penetration, the weld material itself is usually stronger than the surrounding metal. It's usually a lot stronger, in fact. And if a weld breaks, it breaks at the edge of the weld where the material is weaker. So anytime you have a groove, as long as the groove is filled, it's going to be stronger than the material was before. But when you have a fillet weld, then you actually have to design the size of the weld and the material and all that. So anyway, here's my 2 fillet weld beads. And so the centroid of this weld pattern is going to end up being 4 inches down from the top, or 4 inches up from the bottom, and will be 5 inches over. I know this is bad practice. I'm putting dimensions on top of the part, but this is all I needed for it, so there you go. So this is the centroid of the weld pattern. Okay, so now what? Well, I've got a weld pattern. I need to come up with an electrode type. In order to solve this problem, though, I really have to figure out the amount of load in the weld bead. So let's start off with a free body diagram. We need to figure out the loads being applied to this thing and how it's being supported. All right, so first of all, we have a load out here of 1,400 pounds force. Now, you have to be a little bit careful because the way this is drawn, your author shows that the rigid structure from the other view, let's do it this way, supports the shelf, and the shelf actually wraps around both sides of the beam. So there's a motor or something sitting up on top of the shelf with the load, P. But essentially there's going to be a weld bead, let's put that in another color. There's going to be a weld bead, a fillet weld bead here, and a fillet weld bead here on both sides. So in my design, half of that 1,400 pound load is going to be taken by this side, the other half will be taken by this side. At least that's my assumption, that the load is equally distributed. So, if I consider loading about this centroid, let's first of all figure out the position of the centroid. It turns out that this distance to the load, P, is 8 inches. And so from the load to the centroid would be 8 inches plus 5 inches. So this distance here is 13 inches. Now, if I'm going to support this, if I've got my hand at this centroid and I'm applying loads to it in order to prevent it from moving due to this load, what do I have to do? Well, I've got to provide a load upward, which is the direct shear V, but I also have to provide a twist in this direction. Let's use my right hand. I have to twist in this direction in order to prevent this load from causing a rotation about that centroid. So I have to consider both the shear and the torque, or the moment load. Okay? So if you sum forces in the y direction, it's pretty straightforward. The shear load obviously is 1,400 pounds, and once again, I have not divided this among the two sides yet, but it's just equal to P, that's easy. Summing moments about the centroid, if those moments are 0, which is what we want a static situation, then the torque that I have to apply here would be 13 inches multiplied by 1,400 pounds. And that torque is 18,200 inch-pound force. That's the amount of torque I've got to apply at this centroid. Now, what can apply that at the centroid? Just a weld bead. Okay, now, your author has several different cases that he shows in the text for different weld bead patterns that we can solve, because the geometry of the weld bead pattern makes a difference in the solution. So, on page 653, figure 20-8 has 9 different weld patterns that we can actually design and use. Now, which case does this look like? Well, let's see. We've got 2 lines with load off-center. Well, that looks essentially like case 3. If you look on page 653, you'll see that case 3 looks the most like this. Now, you have to be a little bit careful here, because your author shows bending and torsion as 2 different loads. Is this a bending or a torsion load? Well, it's relative to the pattern itself. Okay, so since this load is offside, then basically this is a torsion pattern. You're trying to torque that pattern. It's not a bending load. If it was a bending load, the load would have to be out here, out from the plane of the board, pulling and pushing on the weld bead, not torquing the weld bead. Okay? So the case is definitely case 3, but the loading is torsion loading as far as we're concerned. Okay, so let's continue. The next step is to draw or understand the loading that's occurring in a little more detail. So let me draw the piece again. And due to the shear, there would just be direct shear in the weld bead. It's going to be in both weld beads, obviously. That's good enough. And this force F, this shear, is equal to the shear loading divided by the area of the weld, where the area of the weld is somewhat of a misnomer. It's more the length of the weld. Where did your author put it? Here we are. Page 652 has a table, and that table is not denoted as a table, but it's very important. It's actually 4 equations. Equation 20-4 through 20-7. There's type of loading, direct tension or compression, direct vertical shear, bending and twisting. This is obviously direct vertical shear, and so what I'm doing here is I'm using equation 20-5 in order to calculate the magnitude of the direct shear in the weld bead. So the shear load, V, is 1,400 pounds. Now, yeah, I'll wait until the end to divide this in two, but anyway, let's start off with the load, which is 1,400 pounds force. The area of the weld, what is that? Well, that's just the length. That's what length? That is this length here, plus length, this length, because these two lengths, the lengths of these weld beads, are taking the load. So these are each 10 inches. So the total length of weld taking the load is 20 inches. So this is 70 pounds force per inch. Each inch of weld bead has to take 70 pounds. That's how much it has to support. So that's the shear load everywhere. The next step is to figure out what's going on with the moments. Now, just like the bolted connection that we saw a minute ago, the loading from direct shear is usually not as large as the loading from moments. So if we draw this again and consider what's happening, the load P causes a twist or a torque about the centroid that has to be supported by the weld bead. So if we were to look at the components, what you would do is you would take a line from the centroid out to the weld bead. Once you do that, then sketch the direction of the load. Now, what kind of load is this going to be? Well, this is going to be a torsion type load. Okay, the top and bottom are easy to deal with, but the key to understanding this is that the torsion load acts at right angles to the line from the point to the centroid. In other words, if I were to draw a line out here, then I would have to make a perpendicular shear load in order to describe what's going on at that point. That's right here, right? The shear load due to the moment is in this direction. Now, this is load applied to the beam in order to support it. It's a result of this moment that has to be supported by the weld. Okay? Continuing this, if we drew lines out to various points, then the shear loads would be at right angles everywhere. Okay? I haven't drawn the lengths of the shear load to indicate anything. I'm just trying to draw direction here. So it's apparent that, for example, this shear load here has components in the vertical and horizontal directions. Those components have names. This is a torsional force essentially in the vertical direction, and this is a torsional force in the horizontal direction. Now, your author has some equations to help with this. Essentially, it's TC over J. When your author gives you the equation 20-7, he gives it to you this way. He says that for twisting, the force due to twisting, F, and he uses just F, but I'm going to put F's and T for torsion, is equal to TC over JW. TC is the torsional load. That's this 18,200 inch-pound load. JW is a geometry factor depending on the pattern and exactly where you are in that pattern. Okay, so anyway, this is a total load, right? This is a total force. This would give us the magnitude of this vector. I want the components. Why? Because what I want to do is, just like with volts, I want to figure out where the loads add the most. Wherever the loads add the most, that's where the weld would begin to fail, because that's where the stress would be highest. And so to do that, if I want to add loads together, I'll have to have a common coordinate system. I'll have to have a X and Y coordinate system as we did before. So I'll have to break each of these up into their components. And if you look at it, you can figure out where it's going to be worse, right? Would this point be a point that is critical? No, because look, the shear somewhat cancels. It cancels a portion of the torsion load. How about here? Well, here they both add, but it's a vector sum. There's no component in the vertical direction. Over here, however, there is a vertical component. So I would say that this point and this point, so far, look like the most critical. But it goes even farther than that, because this geometry factor, JW, gets smaller and smaller as you move farther and farther from the centroid. Notice these 2 points are farthest from the centroid. Well, these 4 points are farthest from the centroid in all of the weld pattern. And so one of these 4 points will be critical. Well, it's one of these 2 that has to be critical, because over here, the shear load cancels the torsion load to some extent, whereas here and here it adds. So it doesn't matter which one I analyze, but essentially either this point or this point is the critical point for analysis. So let's calculate FTH, which would be the vertical, I'm sorry, this is not T sub C, this is T times C. So I want C sub V. I want the vertical component. What am I talking about here? Well, what I'm talking about is the distance from the centroid to this point. Okay? And since I want a horizontal force, I'm not being very clear. Since I'm interested in a horizontal force, I'm interested in a vertical moment arm. So this CV is that distance. It's just 4 inches. Okay, because that's just the height from the centroid vertically to this point. So let's go off and compute JW, because we'll need that. JW is a geometry factor, and it's given in your text. Let's see, it is B cubed plus 3BD squared divided by 6. You really have to look at the figure to understand what A and B are. I will try to draw them here. Let's see, B is essentially this distance over here. Let's add it to our figure. This is B, and let's see, the distance D is this distance. Okay, so this geometry factor, like I said, just depends on the weld pattern. And I misspoke earlier, I apologize. JW does not depend on where you are. CV depends on where you are. So CV determines the partially the magnitude of this load. And the farther out CV is, the worse the load is. Obviously, as CV increases, that force increases. So calculating the geometry factor, I'll let you plug in the numbers, but the geometry factor comes out to about 486.7. We're looking at the units. B is a dimension in inches, so this would be cubic inches. And that's JW. And then CV is just going to be 4 inches. And the torque we've already got. So this is 18,200 inch-pound force multiplied by CV, which is 4 inches, divided by JW, which is 486.7 square inches. And so obviously all the inches go away, and we end up with a load in pounds. That load comes out, let's let's see, inch pounds, inches, inches squared. Oh, I'm sorry, this is inches cubed. There we go. So it's not quite all gone. So we'll have pounds per inch, there we go. So our load is 187.0 pounds force per inch. Okay. All right, now that is FT. I'm sorry, I got that wrong. Copied the wrong line. That is actually 149.6 pounds force per inch. Now, if you do the same thing with FTV, then what you'll have to do is use C sub H, where C sub H is the horizontal distance, and that's just this distance right here. So obviously that's going to be, what, 5 inches? Okay, this torque is still the same torque. Now C sub H is 5 inches. JW is exactly as it was before. So this comes out to, here's our 187 pounds force per inch. So there's the vertical and horizontal loads. These are essentially shear loads, and they add to the direct shear. So to come up with the total shear, if you think about it, FTH is here, right? It's in this direction off to the left. It's this component of the shear. And I'm analyzing the upper portion. It doesn't matter if you analyze the upper or lower. You get the same critical quantity. FTV is that shear. And that should be a subscript TV. But the direct shear adds to the vertical component. So what I really want is this resultant load, because there's the total resultant shear load applied at either this point or this point. Of course, the magnitude is going to be the same. The direction will be different because it'll add a little bit differently. But anyway, the resultant load there is what I'm interested in. Now, this one is 149.6 pound force per inch. FTV is 187 pound force per inch. The direct shear F is 70 pounds force per inch. So when you add all these together, the resultant shear is just the square root of 187 plus 70 squared plus 149.6 squared. And what you end up with is about 297.4 pounds force per inch of weld. Now you have to be careful here because so far I've analyzed this assuming that I just have a weld bead on one side, right? I've applied all the load to one side, but this load would be cut in half. It would be about 150 pounds force per inch for each side because we've got two sides to this, right? The front side and the back side. Both of them have two weld beads to support this load. Now, if you look at what the electrodes can take, let's see, electrodes are on page 650, and we're interested in steel electrodes. Let's see, where did he put that now? There's a bridges versus buildings. Oh, I see it. Okay. Page 652, table 20-3 is the one I'm looking for. And all that's listed here are E60 and E70 electrodes. We were to calculate this for building type structure, I believe. Let's see. 9. Yeah, building type structures. Okay. So for building type structures, that's the upper section of the table. And if we use an E60 electrode, then we can have 9,600 pounds per inch. And that's a whole lot more than this 300 or so pounds per inch, which is going to end up being 150 pounds per inch after I divide the load on the two sides of the beam, support structure. So I can choose an E60 electrode at 9,600 pounds per inch. And now you have to be careful here. I don't really like the way this is set up. This can be very confusing. Because this should be listed as per inch squared. Now let me explain why. This 9,600 pounds per inch is pounds per inch of fillet leg size. If you look at a fillet bead from the end view, let's see, your author, yeah, your author has one, here we go. Page 651, figure 20-7, he lists W, let me sketch this. He lists W as the fillet bead size. It's essentially a leg size. And he assumes that you're going to have a fillet bead that is 45 degrees. Okay? So really what we're trying to do is decide, given a material of this weld bead, how wide should this leg be? And we haven't answered that question yet. Really, what this specification gives you is how many pounds 1 inch of weld bead in this direction can take per inch of weld bead leg length. That's probably confusing, but eventually you'll get the idea, hopefully. So really what I'm saying here is that this specification, 9,600 pounds per inch, is per inch of leg on the fillet. Now, every inch of weld bead in this direction coming out from the board can take 9,600 pounds. If you had a leg size on the bottom and top, or side and bottom of this fillet weld of 1 inch, then every inch of that bead can take 9,600 pounds in shear without failing. Okay, that's what that specification really means. So if I want to calculate the size of weld bead W that I need, then what I should do is take the 297.4, say, well, let's do it this way. This is about 300 pounds, right? So 300 pounds force per inch. And 150 pounds per inch is required on each side. So what I'm going to do is calculate the weld bead leg length required as 150 pounds per inch, assuming that I'm going to have this pattern on both sides of the structure, divided by 9,600 pounds force per inch. And let me put it squared, because that's really what this should be, in my opinion. It's per inch this direction, per inch this direction, okay? Which is just obviously the bottom area. What's confusing about this is that you also have to have that same area over on the other piece for this weld bead to work. It's probably why he doesn't list it as per inch squared. In any case, this comes out to about 0.015 or 6 or so inches. That's a 16,000th of an inch bead. Now, if you've ever welded before, you know that this is very impractical. You can't make a bead that small very easily. It's not without special equipment. It's about a 64th of an inch. This is tiny. So what we have to do is specify a reasonable size and say this is going to be, let's say then, an 1/8 inch bead. Okay. Laying down an 1/8 inch bead is hard enough. That's a fairly small bead. But if that's our specification, then the welders won't laugh at us when we give them our drawings and all these fancy calculations. What does all this really do for us then? Couldn't we have just said, a quarter or an 1/8 inch weld bead would work? Well, probably, especially given that the load is only 1,400 pounds. But you want to know for sure that your weld is going to hold, that your design works. And so what these calculations do is they prove to you that even the weakest weld bead should hold just fine. What you might do is actually reduce the pattern size and just have material out here at the ends to save time. But you'd have to take that into account, because then you've got fewer inches of weld length. Anyway, so that's problem number 9, and that's it.